Hey, geometry friends, here we are. Chapter 7.2, similar polygons. We talked about ratios and proportions in the last lesson, and now we're going to apply those to comparing polygons, different shapes. And so let's jump right into to our definitions. Our first definition is what does it mean for shapes to be similar? Obviously, generically, the word similar is they're close in resemblance. They're not exactly the same, but they remind you of each other. Specifically with polygons, it's figures that have the same shape, but different sizes. So for example, we spent a lot of time with triangles where we were trying to prove, well, are they exactly the same? And so are the sides the same? Are the angles the same? And so we learned various proofs on how to do that, side angle side and angle side and all that wonderful stuff that I know you love. And so this is what we would call congruent. Whoops, let me draw that a little better. Call that congruent, exactly the same. So what similar though means is that they are the same shape, but they are in fact different sizes. And so in this case, these would be similar. Notice now you've lost the equal part, and there's simply the similar wave. So the symbol is that little squiggle. And again, so what that means is that you now have different side lengths, though as we'll learn, your angles, in order to have the same shape, it's your angles that matter. And so the angles would all still be the same, but now the sides are not. And it's just like when you resize something like in a graphic arts program on a computer, you take it and you can squeeze it. The shape stays the same, but you can change it to all sorts of different similar sizes. And so that's what we're talking about. So what do we mean then by similar polygons? Well, they're polygons whose corresponding angles are congruent. So the angles are congruent, whereas the sides are merely proportional. Okay, so for example, I'll draw our triangles again. I might have my triangles here. And in this, if these were truly similar, then we might say, well, this is, we'll just do it this way, 60, 60, 60. Actually, let's not do that because then the sides aren't congruent. We'll just say this is 20, this one is 80, and this one's also, actually, I want to make it isosceles either. All right, 20, 70, so that's 90, and so then this one would be, I'm trying to do my math real quick, sorry. Watch, I'm having trouble making up angles here. 20, 50, and 110. All right, that doesn't look right, but who cares? All right, so you got those three angles. If this one is similar to that one, then the angle measurements would still need to be 20 degrees, 50 degrees, and 110 degrees. Okay? Because the angles will always be congruent because it's the angles that form the shape of something. If you have different angles, you get a totally different shape. So the angles will always be the same, but your sides are now different. And so this one's 9, this one's 12, and this one's 10. Again, breaking all sorts of rules by just making up these numbers, but focus on the side lengths. Whereas this one has sides of 3, 4, and 5. Okay, so different side lengths, but congruent angles. But not only different side lengths, but are they, here's the key word, are they proportional? Well, that's going to be the real trick. Can you write a proportion using all the different sides? And so we can check that, and we can say, okay, well, if the ratio of this one is not, one side is 9 to 10 right here, that should be the same ratio of here. Does that equal 3 to 5? And again, you can just kind of look at that and go, yeah, because I can see they're both divided by, oh, wait, actually, we'd have to, yeah. Well, actually, so you would look at that and you say, well, no, these aren't proportional, because if you checked it, if I checked my cross products as we learned in the last lesson, I'd get 9 times 5 is 45, and 3 times 10 is 30. And so if you were answering this question and saying, no, these in fact would not be similar polygons because their sides are not proportional. If we wanted to make it proportional, then we would have to say, well, I can see that basically each 9 divided by 3 is 3, 12 divided by 4 is 3. If I change this one here to 15, then that would make the triangles proportional, because then you would have 9 to 15. Is that the same as 3 to 5? And if you check those cross products, 9 times 5 is 45, and 3 times 15 is 45. So now I can see that those sides are in fact proportional. Though you need to go ahead and check the other side. So something like, let's get the color here, 9 and 12, and 3 and 4. And you could check that as a proportion and say, okay, is 9 to 12, running out of room here, is that equivalent to 3 to 4? And again, if you cross multiply those, you can see they would both equal 36. And so again, we're going to be doing that a lot in terms of trying to identify whether polygons are in fact similar. And again, the angles will be congruent, but you'll need to see, are the sides in fact proportional? Can you express them as equivalent proportions? All right, let's check out similarity ratio. The ratio, which is the ratio of lengths of a similar polygon. So it's basically if you have a similar polygon, what is the ratio of its sides? And it would have to be the same for every single side. So let's use the example of the one I got to up here. Maybe I'll go ahead and redraw it since that got a little exciting. Oops, that got a little messy up there. So we have one triangle here that is 9, 12, and 15. And we have a smaller but similar one that is 3, 4, and 5. What's the similarity ratio? Well, basically, you simply want to compare the sides. So you'd compare the corresponding sides. So for example, I'd want to compare this 3 to 9, the 4 to the 12, 5 to the 15. And if they're similar, I should get the exact same ratio. So you've got 3 to 9, you've got 4 to 12, and you've got 5 to 15. Okay, well, all three of those reduce to 1/3. Okay, so that's not only another way to see if these are in fact proportional, but you found the similarity ratio. The ratio is 1 to 3. That smaller triangle is 1/3 smaller than the big one, or the big one is 3 times bigger than the smaller one. So that similarity ratio, just compare the two sides of the polygon, reduce the fraction, and then you'll have the similarity ratio. And one way of proving checking whether polygons are similar is by seeing if all the sides have in fact, this exact same ratio. Okay, let's get to the questions. So question number 1, what's the difference between similar and congruent? Okay, we pretty much already covered that. Congruent is exactly the same, and it has equal sides and angles. Okay, and so again, an example would be two shapes that are exactly alike in terms of sides and angles. Okay, where similar means same shape. Okay, equal angles, but proportional sides. Okay, and that again would be something more like, okay, where they both have the same angles here, but the sides are clearly not the same. Okay. Number 2 asks, in similar polygons, what changes, the side lengths or the angles? Okay, again, we're just hammering this to death just so that you can get it clear, but the angles stay the same. Angles are the same, whereas the sides change. So again, you can look at these two polygons that I've drawn. That this angle here would be equivalent to that angle. This angle here would be equivalent to that angle. This one to this one, and finally this one here. Okay, so the angles stay the same, but the sides change. Okay, not both. Question number 3. What's the similarity ratio for two squares with side lengths 5 inches and 65 inches? Okay, so we went over that. You're simply going to make a fraction. And it doesn't really matter which one you put first. Since in the question it says 5 inches and 65 inches, I'm going to go with that order, even though I drew it in a different order. So it would be 5. I would simply say 5 to 65. Okay, that's your similarity ratio, though you then need to reduce it. And so 5, you can reduce both of those numbers by 5. And so that's the same as 1 to 13. So the similarity ratio in this case would be 1 to 13. And I'd expect all sides to have that same ratio. And finally, last one, number 4. How do you check for similarity? And again, I kind of did this in the when I was defining similar polygons, but let's do it again. There's kind of a number of ways you can check, but quick way is to I'll say there's 2 ways. You can set up a proportion and see if your cross products work, or you can see if they have the same similarity ratio. Let's go ahead and just do both. So first of all, we can set up a proportion. And there's lots of ways to do that, but in this case, I'll just do a ratio of the sides to one another. And so I'll say 4 to 12 would have to be the same as 6 to 16. Okay, that would have those would have to be equal. And so the quick way to check that would be to cross multiply. Okay. Let's just see that. Actually, let's see. Maybe that's not the best way. We'll wait on that. Let's just go with the sides ratio. Well, actually, no, that works. 4 to 12. Sorry, forgot what I was doing here. 4 to 12 is that the same as 6 to 16. And so let's go ahead and do our cross products. Oops, come back to me. Okay, 6 times 12 is 72. And then 4 times 16 is, I believe, 64. Okay, and so you can see they are not equivalent, and so you'd say these two shapes, in spite of how they look, those two shapes are not proportional. The other way that we would check it is that we would do the ratio of the sides. And so I could say, is 4 to 6 equally the same as 12 to 16? And then you could simply reduce that. Well, 4/6, that reduces to 2/3. And 12 over 16, that reduces to 3/4. So in other words, these two have a similarity ratio of 4 to 6, whereas these have a similarity ratio of 3 to 4. If all sides don't have the same similarity ratio, then no, you are not, or we should say, not similar. Okay. Whereas let's go ahead. I gave the second example as a way of showing when it does work. Let's write the proportion. 4 over 12, is that the same as 6 over 18? Okay, well, if we cross multiply, check our cross products, what you're going to get is 4 times 8 is 72. And 6 times 12 is 72. And so in this case, they are in fact similar. Or if we go ahead and check for the ratio, we can say, okay, is 4 over 6 the same as 12 over 18? Well, 4 over 6, that reduces, as we already know, to 2/3. And 2 and 18, we can divide both of those by 6. That also reduces to 2/3. So there, the similarity ratio is the same. So we can say these two are in fact, oops, make the squiggle, right? They are similar, whereas the ones above are not. You don't have to do it both ways. You can decide either one. You either write the proportion and do your cross multiplication, or you can just kind of write them as fractions and reduce them and see if you get the same similarity ratio. Alrighty, so that's similarity in polygons, and we'll be discussing that in class and look forward to working on it with you guys. See you soon.